Hi all. Today we are going to discuss about the mechanical strain gauges. Coming to the mechanical strain gauge, uh, it involves a mechanical means of magnification. That means extensiometer will be given, and which is commonly used in mechanical strain gauges. So type 1 will be Berry type, and second type will be Hagenberger type. Two types of mechanical strain gauges are there, where the extensiometer is used for the magnification purpose. Let us see what are the parts of a extensiometer and how the mechanical strain gauges are going to work with the extensiometer. See, we are going to take on mechanical specimen, and which is going to subjected to the tensile force on both sides, and there will be specimen, and which is pointed at 2 points. You can see there is a magnifying lever will be there at the point, and that is attached to the dial indicator, where we are going to get the readings of the deformation of the particular mechanical specimen. So using this gauge points and magnifying lever and dial indicator, you are going to get the correct output of the deformation that is subjected to the tensile force. Coming to the optical strain gauge. So optical strain gauge, basically it is used for the mechanical system, as well as for it is for magnifying some mechanical components. Whenever there is a strain is happening in a uh, mild steel, or it may be a transparent material, or it may be a copper material, it may be bronze material. Whenever there is a strain is going to occur, that can be measured by a means of mechanical system or by a optical system. So it is a optical strain gauge is a combination of both mechanical and optical system. That means extensiometer and autocollimeter both are used as a magnifying purpose, and through which we can going to measure the strain that is occurred in a specimen. And it can be used to measure a 2 micrometer per meter and a gauge length up to the 250 mm. That is the range of the optical strain gauge. This is the Tuckerman optical extensiometer. In the figure you can see there is a objective lens, and there is one specimen which is under a tensile load, and that specimen is screwed to the prism adjustment screw, and there is one extensiometer is there, and there is a knife edge. And as I said, optical extensiometer and mechanical extensiometer both are there here, and they are used to magnify the object, and through this one we are going to measure the deformation that is going to occur in the specimen. There is an eyepiece, and there is a reflector for the light that is passed to the objective lens, and where we are going to get the uh, deformed image of the material that is screwed to the prism adjustment screw. And using the extension meter, we are going to transfer the deformation into the optical microscope, where we are going to get the deformed image of the specimen. And we can see there is a eyepiece, and there is a adjustable eyepiece is there. We can adjust the magnifying image of the particular specimen. And we can see there is a nominal length of gauge is distance from the knife edge to the point of a lodge lozenge, and the lozenge acts as a mirror, and the distance between the fixed edge and the lozenge changes due to the loading, and lozenge rotates, and any light falling on it will be reflected, and the function of autocollimeter is to send the parallel rays of light and receive back the reflected light beam from the lozenge on the optical system. This is how the system is going to work. Coming to the electrical strain gauge, any change in a strain produces some change in the electrical characteristic. That means the electrical parameters such as capacitance, inductance, or piezoelectric, or resistance gauges. So these parameters are going to vary as the strain produced in the specimen. And the change can be magnified using the electronic equipment, and different types of strain gauges that are going to measure the capacitance, inductance, piezoelectric, and resistance gauges. What are the materials used for the electric gauges? That means alloys of nickel, copper, nickel, and alloys of chromium and iron, and other elements of some small percentages of other elements also included. Basically, these are the materials that are widely used in electronic gauges. Gauge resistance varies from 60 ohms to the 5000 ohms. Current current gauges for long periods is around 25 microamps to 50 microamps. This is the range of the electrical gauges. Electrical strain gauge basically having a resistance of a conductor that is given by R equal to rho into L by A, and different types of electrical gauges are unbonded type, bonded type involves a wire and a foil type, and a semiconductor or a piezoresistive strain gauges. These are semiconductor means a piezoresistive strain gauges will be there, and these are going to sense the very small changes in a strain that is occurred in the specimen. These are the different types of electrical gauges basically we are going to use. Unbonded type means the wires are unbonded, they are separately wounded on two uh, holding specimens A and B, and there will be a fine wire that is going to wound on a specimens and to bridge the circuit. And whenever the specimen is under tensile force, and that deformation is going to convert into equivalent form of electrical resistance, and that's how we are going to measure the strain in the specimen. And this is again a circuit for a electrical strain gauge. You can see there is a electrical wire 1 and electrical wire 2 and wire 3 and wire 4 are there. Four types of different resistance with a fixed base, and there is a movable platform is there. And this is a Wheatstone bridge network. There are four resistance and there is a galvanometer. Whenever there is a change in the deformation, that can be sensed by resistors, and that's how we are going to vary the or measure the different parameters such as inductance, capacitance, and deformation that is going to occur on the specimen. And this is the bonded resistance strain gauge. Whenever a strain gauge is used for a measurement of strain in the material, a bonded type, that means the whatever the wire grid is there, that is bonded, and there will be insulating material that is attached to the measurement to be done. And when there is an appropriately shaped piece of resistance material and it is bonded to the surface of the material to be tested, then it is called as a bonded strain gauge. In the figure you can see there is a thin wire in the form of a grid pattern, and is cemented between the thin sheets of a material. A thin wire in the form of grid pattern is cemented in between the thin sheets of insulating materials such as paper or plastic are used as insulating materials, and the strain gauge may be a thin metal of foil. Strain gauge that is used is usually of a thin metal foil, and that is wounded with cement material. The resistance type of electric strain gauges is the most popular device used for the measurement of strain. In this case, electrical resistance of a gauge proportionally changes when there is a strain is going to occur. That means basically electrical gauges are going to work on a principle that whenever there is a change in the strain, that means whenever the material is going to deform, so this is proportional to the electrical resistance. As strain changes, the electrical resistance also changes. So that's how we are going to measure the proper deformation or a deflection of a material. These gauges exist in the following forms. That means different types: wire type, foil type, or semiconductor piezoelectric strain gauges. As we discussed, there will be wire type, there will be bonded type, or foil type strain gauges, or piezoelectric strain gauges that are going to be used as a strain measuring instruments. Wire type strain gauge is usually made up of a very thin wire having a diameter of 0.025 mm, wound into a grid shape as illustrated in the figure. The grid is cemented in between the two pieces of thin paper, and the insulating materials are acting are used ceramic as well as plastic backing. This will facilitate easy handling of a strain gauge. The gauge is further bonded securely to the surface of the member on which the strain has to be measured using the cementing material. That means in the figure you can see there is a bonded wire type of strain gauge is there that is cemented with help of a plastic backing or ceramic materials, and whatever the deformation is going to occur, that equivalent strain is converted into the electrical resistance, and that's how the measurement is done. Similar to the body type, foil type is also the thin foil of electronic wires are cemented to the measurement to be done, and that surface is uh, clean before going to attach the foil type of a resistance strain gauge. For high temperature applications, epoxy is filled with a fiberglass, and which is going to measure the very small deformations in the material. These gauges are manufactured by printing them on a thin sheet of metal alloy with an acid resistant ink, and the unprinted portions is etched weight. That means so these materials are going to measure the very sensitive deformations, and that's why these are manufactured with a printed type. That means we're going to use a metal alloy of thin sheets, and it is superposed with acid resistant zinc. This will give a very thin type of electronic foils. So these foil type resistance gauges are going to offer advantages such as improved hysteresis, a better fatigue life, lateral strain sensitivity, and they can be fixed on fillets and sharply curved surface because they are thin and have a higher flexibility. These are also known as a metallic gauges. Foil type resistance strain gauges is shown in this figure. As seen in the figure, the foil type resistance gauges are for different thin foil types and attached with the help of electronic ink. Coming to the third type, piezoelectric strain gauge. In the figure you can see there is a packing material, the semiconductor element, and a copper lead is there. And semiconductor gauges are cut from single crystals of silicon or germanium, and this type of gauge contains precise amounts of impurities like boron, and which impart certain desirable characteristics. The backing or bonding materials and mounting techniques used for metal gauges are employed here. When the material is on to the semiconductor gauges or bonded is strained, the current in the semiconductor material changes correspondingly. That means whatever the deformation is there, and at that time the strain is measured with the help of semiconductors. When electronic or electrical resistance of a gauge increase due to the tensile strain, then it is a positive or a p-type semiconductor gauge. Semiconductor gauges also possess certain disadvantages. That means the output obtained in semiconductor gauge is non-linear in nature, and strain sensitivity of gauge is temperature dependent, more fragile when compared to the wire or foil type element, and it is expensive compared to the ordinary metallic gauges. These are the disadvantages we come across semiconductor type gauges. Bonding of gauges. The following are the steps to be followed while bonding the gauge to the specimen. First, we have to wash the hands with the soap and water. The working desk area should be kept clean, and later tool should be washed with a solvent or degreasing agent. That means degreasing. Whenever there is a greasy or a sticky material is there, we have to apply the degreasing agent so that it will be cleaned. And second one, the folder containing the gauge should be opened carefully. A bare hand should not be used to grasp the gauge. Tweezers can be used to hold the gauge and do not touch the grit. Third precaution is place the gauge on a clean working area with a bonding side down. Then whatever the surface area to be bonded, that has to be down in facing the attachment. Fourth one, use a proper length, say about 15 centimeters of cell phone tape to pick up the strain gauge and transfer it to the gauging area of the specimen. Align the gauge with the layout lines and press one end tape to the specimen, and then smoothly and gently apply the whole tape and gauge into the position. And fifth precaution, lift one end of the tape such that gauge does not contact the gauging area and the bonding site is exposed. Apply the catalyst evenly and gently on the gauge. And the sixth precaution we have to take is apply enough adhesive to provide a sufficient coverage under the gauge for the proper adhesion. These are the 6 measures to be followed while adding the or adhesing the for types of gauges. Some iteration may be required in determining the sufficient coverage. Place the tape and gauge back on the specimen smoothly and gently. Immediately place the thumb over the gauge and apply firm or steady pressure on it for at least a couple minutes of time. Coming to one of the important factor, that means the gauge factor or strain sensitivity. Gauge factor is most important parameter of the strain gauges. It is a measure of the amount of resistance change for a given strain and therefore serves an index of strain sensitivity of a gauge. Mathematically, uh, basically resistance is given by rho L divided by A, and the strain sensitivity or gauge factor is given by F equal to delta R by R divided by delta L by L. That means the ratio of change in the resistance to the change in the length. That is nothing but a sensitivity, strain sensitivity or a gauge factor. The gauge factor is the ratio of change in the resistance to the change in the gauge length. A higher gauge factor makes the gauge more sensitive and electrical output obtained for indication and recording purpose will be greater. That means the higher gauge factor that is going to give the greater that means whatever the sensitivity is there, that is more precise, most accurate when gauge factor is going to high. The gauge factor is applied by manufacturer and it may vary from 1.7 to 4 depending upon the length of the gauge. As we know that gauge factor is going to vary depending upon the gauge length. So whenever there is a change in the gauge length, depending upon the gauge length, the gauge factor is going to vary from 1.7 to 4. Basic Wheatstone resistance bridge methods of strain measurement. Electrical resistance of strain gauges usually highly sensitive Wheatstone bridge circuit for the measurement of strain, consisting of 4 resistance arms with a source of energy and detector as shown in the figure. You can see we already seen the Wheatstone bridge network with 4 resistance wires R1, R2, R2 and R4, and there will be supply of electric current I1, I2, I3 and I4, and there is a bridging at the point of B and D, and there is a ammeter and a voltmeter, and this is the basic circuit for a Wheatstone bridge. A basic principle of a bridge may be applied in 2 different ways, that means null or a deflection method. So 2 methods are used, null or a deflection method. That means from the Wheatstone bridge network we know that R1 by R3 equal to R2 by R4. That means ratio of resistance at the point 1 and 3 are equal to the ratio of resistance at the point 2 and 4. Suppose if any resistance change, it will be unbalance the bridge and voltage will appear across the B and D, causing a meter reading to change. The meter reading is an indication of a change in the resistance, and actually it can be utilized to compute this change, known as the deflection method. We have seen the Wheatstone bridge network, the resistance based bridge arrangement for a strain measurement. We can see there is one specimen is there, and that means 2 forces are applied in a tensile way. That means longitudinal forces are applied at the both ends, and that is connected to the Wheatstone bridge network, and through the resistance R3 and R4, and there will be 2 arms, arm 1 and arm 2, and at the point 2 we are going to get the different strain measurements, that is that has to be measured on a test specimen. Coming to the temperature compensation, gauge factor of a strain gauge is affected by a temperature owing to creep, and the resistance of a strain gauge elements vary with the change in the temperature. Strain may be induced in the gauge due to differential expansion between the test member and strain gauge bonding material. That means whatever the strain is there, that is going to induced, or it is going to vary depending upon the strain gauge bonding material. And different types of methods are adjustable arm compensating gauge and self temperature compensating gauge. These are the 2 methods that are going to use in a temperature compensation. And the figure C, you can see there is a compensating gauge is there, that is going to acting as a resistance 2 material, and resistance 1 material is attached to the test material, and there are another two resistances, the R3 and R4. Through the four resistances we can measure the deformations or strain in the material. If the strain gauges in the arms 1 and 2 are alike and mounted on a similar material, and if both gauges experience the same characteristic shift, that means delta RT caused by temperature change, then R1 plus delta RT equal to that means whatever the ratio of resistance change, that means R1 plus delta RT divided by R2 plus delta RT, that is equal to the change the resistance at the point 3 and 4, that means R3 and R4. It is clear that any changes in the resistance of gauge 1 due to the temperature is cancelled by similar changes in the resistance of gauge 2, and the bridge remains balanced and output unaffected by the change in the temperature. And coming to temperature changes, it is change usually measured by observing change in the temperature depending upon a physical property, and direct comparison is difficult in case of temperature change. In practical, the thermometry or temperature is measured using help of electronic resistance. Temperature is instead gauged by its effect on the quantities such as volume, pressure, and electrical resistance or radiated energy. And common temperature sensing techniques, that means two methods, physical dimensions, that means liquid in glass thermometers, and bimetallic elements that are going to used as temperature sensing techniques. And the change in the gas pressure or vacuum pressure, whenever there is a change in the gas or vacuum pressure, one will be constant, that means vacuum gas thermometers are used. Whenever there is a gas pressure, vacuum pressure are in a constant condition, and the pressure thermometers are used when there is a gas, vapor or liquid filled conditions are there. Change in the electrical properties such as resistance thermometers, RTD or PRT are used, and thermistors, thermocouples, and semiconductor junction sensor. These are the various types of elements that are going to measure the electrical properties. And change in the emitted thermal radiation, thermal or photon sensors are used. Total radiation pyrometers are used, and in case of change in the emitted thermal radiation, the optical or two-color pyrometers are used, or infrared pyrometers are used. If any change in the chemical phase, then fusible indicators or liquid crystals or temperature reference fixed point cells are used to measure the deformations. Temperature measurement by electrical effects. Whenever we are going to measure temperature based strain measurement, and they are very convenient method of temperature measurement, and they provide a signal that is can be easily detected, amplified, or used for the controlling the purposes or processes, and accurate result when calibrated or compensated. These type of electrical sensors are used, or electrical method is used to measure the electronic strain measurement. RTD, that means resistance thermometers. Electrical resistance of a material varies with the temperature, we know that, and resistance elements sensitive to temperature were the first made for metals. Resistance measuring elements are such as nickel, copper, platinum are used, and sometimes silvers are used. Measuring device using an element of this type is referred as a resistance thermometer or a resistance temperature detector. That's why it is called as a RTD, resistance temperature detector. Different types of requirements. Material should be permit a fabrication. Thermal coefficient or resistance should be high and constant. Corrosion resistance, and it should go under phase change within temperature ranges, and provide a reproducible or consistent results. And these are the basic requirements for the measurement of a RTD. Basically, the resistance temperature detectors having the relation between the resistance and temperature, that means RT equal to R naught 1 plus a of t minus t naught plus b into t minus t naught square. That means where RT is equal to resistance at the temperature T, R naught is the resistance at the temperature at T naught, and A and B are the temperature coefficient of a resistance depending. That means this relation is going to bring a relation between the resistance and temperature. This is the RTD construction. There is a resistance element is there, and insulation support material is there, and protective sheath is there in order to provide a compact relation and a compact space between the resistance element and the insulating material. And in the figure you can see there is a well and an element connecting here is there in order to measure the temperature based resistance. The resistance wire is wrapped around a mica strip and sandwiched between the two additional mica strip. The RTD may be used directly, but with the permanent installation with the corrosion and mechanical protection is required not to use the RTD. And instrumentation, the bridge circuit is normally used to measure the resistance change in the thermometers, and leads of appropriate length is required to measure the change in the resistance, and lead resistance must be low as possible when compared to that of a element resistance. That is how we are going to instrument the materials. In the figure you can see the Siemens 3 lead arrangement is there in the first figure, and second figure calendar force lead arrangement, and third one is a floating potential arrangement. And these are the different types or configurations that are used for the RTD. Methods of compensating lead resistance. A Siemens 3 lead resistance, it is the simplest corrective circuit, and at the balance condition the central lead carries a no current, and resistance of other two leads cancelled out. This is basically for Siemens 3 lead arrangement. And a floating potential arrangement, the extra lead is used to check the equality of the lead resistance. And for thermoelectric effect, Seebeck effect, when two dissimilar metals are joined together, and electromotive force EMF will be exist between the 2 points, say A and B, which primarily a function of junction temperature. That means T, junction temperature. That is nothing but a Seebeck effect. And one more effect is Peltier effect. If the two metals are connected to an external circuit in such a way that current is drawn, the EMF may be altered slightly owing to phenomenon. That means it is nothing but a Peltier effect. Coming to the Thomson effect. Further, if a temperature gradient exists along the either of both metals, the junction EMF undergoes an additional slight alteration. That is Thomson effect. These effects, Seebeck effect, Peltier effect, or Thomson effect, are going to change the that is the strain measurement. That means whatever the strain we have to measure, we will get some alterations, or we are not going to get the correct outputs due to these effects. And thermocouple principle, we have two junctions. Junction 1 with the temperature 1, junction 2 with the temperature 2. There will be two metals, metal A and B, and there will be 2 points, say A and B, where the two junctions are attached with two EMFs, E1 and E2. Let us see how it will work. If dissimilar metals are joined, an EMF exists, which is a junction of several factors including temperature. When junctions of this type are used to measure the temperature, they are called as the thermocouples. The principle of thermocouple is that if the two dissimilar metals A and B are joined to form a circuit as shown in the figure, it is found that when the two junctions J1 and J2 at different temperatures T1 and T2, small EMFs E1 and E2 are generated at the two junctions. This is the basic principle of thermocouple. The net EMF is a function of two materials used to form the circuit and the temperature of two junctions. The actual relations, however, are empirical, and temperature EMF data must be based upon the experiment. It is important that the results are reproducible and therefore provide a reliable method for measurement temperature. That is the basic requirement for a thermocouple. It should be noted that Two junctions are always required, and one which senses the desirable or unknown temperature is called as a hot or a measuring junction. The other junction maintained at a known fixed temperature is called as a cooled or a reference junction. Two junctions, one will be measuring junction and other will be reference junction. Reference junction is going to act as input, and measuring junction is going to act as output, where we are going to get the measurements. Laws of thermocouple, law of intermediate metals, or law of intermediate temperatures. So let us see what is the law of intermediate metals. It states that insertion of any intermediate metal into thermocouple circuit will not affect the net effect EMF, provided the two junctions introduced by a third metal are at identical temperature. In the figure you can see metal A and B. It says that any insertion of intermediate metal into thermocouple circuit will not affect the net EMF produced until and unless when the two junctions introduced by third metal are at a identical temperature. That means the temperature should not change. We should maintain the identical temperature. Then only we are going to get the correct EMF without any alteration. And coming to the law of intermediate temperatures, state that if a simple thermocouple circuits develops an EMF E1 when its junction are at T1 and T2, and EMF E2 is produced when its junction is at a temperature T2 and T3, then the same circuit will develop an EMF that is equal to E3 equal to E1 plus E2, provided the junction temperatures are at a T1 and T3. And that means in the third figure you can see the temperature junctions T1 and T3. Due to this one, we are going to get the EMF E3, that is equal to the EMF produced at the E1 plus E2. And material and construction for this one, and we should process following properties. That means a linear temperature with a similar EMF relationship, and it should produce a high output EMF. Resistance to the chemical change should be highly desirable, and stability of EMF should be there, and mechanical strength should be properly maintained. Different types, that means rare metal types using a platinum or a rhodium, iridium, and base metal types. These are two types, different types of thermocouples. You can see the twisted wires, junction type, and these are the different types of thermocouples. Element with bed insulators, these are again different types of thermocouples you can see. And in the figure you can see measurement of thermal EMF. In the figure you can see there is a specimen is there. It is connected to the junction 1 for the measurement. Junction 1 is going to acting as an input, and J2 is a reference junction. There will be a thermometer to detect the reference junction temperature, and with a potentiometer we are going to measure the thermal EMF. And the magnitude of EMF generated by a thermocouple is around 0.01 to 0.07 millivolts per degree Celsius. Advantages and limitations: less expensive when compared to the RTD, and convenient for measurement temperature at a particular point. And the limitations involves inaccuracy, protection against the contamination, and it should be placed at a particular place. These are the limitations. Coming to the pyrometers, pyrometers again the temperature sensitive devices. When temperature to be measured at a high and physical contact with a medium to be measured, and then it is impossible, then the thermal radiation methods or optical pyrometers are necessary. Their pyrometers are used when the corrosive vapors or a liquid would be destroy the thermocouples and RTD. These measure the heat emitted and reflected by a hot object. Thermal radiation is the electromagnetic radiation as a result of temperature. And the operation of thermal radiation pyrometers are based upon the black body concept. And the total thermal radiation emitted by a black body per unit area is given by Stephen Boltzmann law. A principle used for radiation temperature measuring devices, that means total radiation pyrometry. It involves total radiant energy from a heated body is to be measured, and again it involves the radiation parameter is to receive the maximum amount of radiation energy at a wide range of wavelengths that is possible through this pyrometry. How to select the radiation pyrometer? This is going to involve the measurement of spectral radiant intensity of radiated energy from a heated body at a given wavelength, and the optical pyrometer uses this principle for selective radiation. Again, this receives all the radiation from a hot body and focuses it on a sensitive temperature transducer like a thermocouple, resistance thermometer. It involves a radiation receiving element and measuring devices to indicate the temperature. And a lens is used to concentrate total and radiation energy from a source, and it will project it on temperature sensing devices where you are going to measure the temperature changes. Coming to the optical pyrometry, it uses the method of matching the temperature as the changing the measurement. A reference temperature is provided in the form of electrically heated lamp filament, and two methods are followed. Let us see. This is optical pyrometry. The figure you can see in the eyepiece. One film is the red film to uh, filter out the radiation hazards, and there is a lamp is there, lamp source that is connected to the rheostat, battery, and ammeter, and the radiations from the lamp are passed to the absorption filter, and that is projected to the optical lens, objective lens. Again, there is a temperature source where we are going to measure the temperature change. A filament temperature background, when the filament temperature is too high, it is going to give a heavy darker radiation zone, and the C type you can see the corrective filament current, that means two splitted wires are there through which we are going to get the correct filament current. And this is the principle where how the radiation is going to projected to the projecting receiver temperature sensor through the lens, and there is an eyepiece to measure the how the temperature is going to change. There is a balance established between energy absorbed by receiver and that is dissipated to the surrounding. Receiver equilibrium temperature becomes the measure of source temperature with a scale established by the calibration. And the mirror type radiation receiver is another type of radiation pyrometer as shown in the figure. Here the diaphragm is used with a mirror to focus the radiation on the receiver. The distance between mirror and receiver may be adjusted for the proper focus. Since there is no lens, the mirror arrangement is advantageous, and absorption radiation effects are absent in this type of diaphragm type of pyrometers. And this is about the optical pyrometers. And temperature measuring, strain measurement, electrical strain gauges. These instruments or devices, these are going to measure the strain, whatever the strain has to be measured on mechanical components. Through these devices, we can easily measure the strain measurement. And so again, electrical strain gauges are efficient. They are going to give the correct outputs, and the results are precise every time. And optical strain gauges are cost wise it is very expensive, and the maintenance is very high, and there should be a dark setup for a measurement of change in the deformations, and temperature based devices that are going to help in the temperature applications and the mechanical heat treatment process. Whenever there is a deformation occurs in a mechanical components, when we have to measure the strain induced in the material, then these optical pyrometry type of devices are used to measure the strain gauges. And this is all about strain measurement. And thank you all, have a good day.